Good morning everyone. Myself N.Uday RanjanGoud, working as Assistant Professor in Department of Aeronautical Engineering, MLR Institute of Technology. Today we are going to have a session in the subject Aerospace Structures. So already we have completed 4 modules and this is the 5th module. So the title of this topic is Plates Subjected to Distributed Transverse Load Q. So we have already discussed in the previous sessions that when thin plates are subjected to bending and when thin plates are subjected to bending and twisting, so how the plates will behave under bending and twisting loads. Now in this session, we are going to see the thin plates behavior and whenever they are exposed to transverse load. So the expected learning outcomes in this module are the students are able to analyze the effect of distributed transverse load on thin plate. The students are able to develop general differential equation for the solution of a thin plate. So the general differential equation for the thin plate is a very important equation, because from this equation we are going to find out how we can evaluate deflection and how we can apply the boundary conditions. So finally there are different boundary conditions are there. So different boundary conditions can apply for this general differential equation and we can get the solution for the deflection of the plate. So in this slide you are able to see the diagram and this is the general normal configuration here. So in this, so we have a thin plate and which has, again in the 3-dimensional analysis, if you see there is x-axis, y-axis and z-axis system is there, and let us assume that the thickness is very small and we can see the dimensions. There are 2 dimensions. We can consider this as A and this is B, and the dimensions are A cross B and with the thickness T. So thin plate, this is a general configuration of a thin plate. It is normal configuration of a thin plate. Now on this thin plate, let us apply a distributed transverse load Q. So now we are applying, now this distributed transverse load means it is a normal. We have to apply normal to the axis of the plate. So this distributed transverse load we have applied like this on the top of the plate. Now when you apply distributed transverse load on the top of the plate like this, now how the plate will behave and what are the changes in the dimensions that will occur. It may be the changes in dimension A, it may be the changes in dimension B, or it may be the change in dimension T. So we are going to analyze this behavior of thin plate when it is subjected to transverse load Q. And now along with bending, in the previous sessions we have seen bending, we have seen twisting. Now we are going to develop a general differential equation now along with the bending case, along with the twisting case, and now the plate deflections are used to develop the general differential equation for a thin rectangular plate which is subjected to transverse load. And we follow some assumptions that plane sections remain plane. So when the plane sections remain plane, we know that the shear strains gamma xy, gamma xz and gamma yz are 0. That means the third dimension we are not considering. So whenever you consider plane section and the z containing terms, the shear strains can be made into 0. And the transverse load, now we are applying the transverse load. So this transverse load also produces transverse shear stresses. So the transverse load, whatever we are applying here, it indirectly produces the transverse shear forces also. And these shear forces induce this shear stresses. The transverse load produces transverse shear forces and which in turn produces the transverse shear stresses. Okay. So this is a general configuration of a thin plate. Now the thin plate we have seen here and the similar. Now let us consider an element of this thin plate, and when you maximize this element and when you try to draw it on the x-axis, y-axis and z-axis system, which includes dimension A, dimension B as well as the thickness of the plate T, and in the maximized position you can see the diagram like this. Okay, so this is a element of the thin rectangular plate, but we are viewing this as a image, that is enlarged image. Okay, so now let us assume that now here understanding this diagram is very important for this derivation, because whatever the derivation we are going to do, what are the steps we are going to involve here, completely we are going to write it from the diagram. So it's very important for every student that you must understand the diagram first. What are the notations we are giving, what are the moments we are applying, and what are the shear forces we are applying, on which edge which moment is applied, and what is the corresponding moments on the other edge opposite to it. So all these are very, very important. So I recommend students first to understand this diagram, take time to understand this diagram, and then after that we can proceed for the derivation. So this is a small element and in which the many moments are represented. So first let's try to understand this diagram first. Okay, so first of all, and we are considering plate and which has a rectangular cross section. Okay, and now first let us assume the edge, that is length along x-axis is delta x and the length along y-axis is delta y. Okay, so now, and let us assume the thickness of the plate is t, and from the center of the plate or from the neutral axis, you can assume that half of the thickness is above and half of the thickness is below. So the total thickness is t and it is divided into t by 2 and t by 2. Okay, now after this, let's go for the moments. So now at the center of the plate on this one, so it is a dotted edge which is showing here, inside edge, and let us assume a moment of mx. So mx is nothing but bending moment applied in x plane. Okay, so and on the same edge opposite to it, so that means this edge, and there is an incremental length along, that means whenever the plate the load moves along this x-axis, so there is an incremental moment, and let us assume that incremental moment as mx plus dou mx by dou x into delta x. Okay, so similarly, and you can observe one more thing, that is the moment along this axis is nothing but what, my, and opposite to that edge, that is on the opposite edge, let us assume the moment as this one, that is my plus dou my by dou y into delta y. Now it is very, very important why we are taking the incremental length with respect to x and with respect to y. That means as you move along x-axis, we take the incremental length as dou mx by dou x into delta x, and as we move along y-axis, we take the incremental length as dou my by dou y. Okay, so these are the moments which we have. First one is mx, second one is mx plus dou mx by dou x into delta x, and the third one is my bending moment which is applied in y plane, and on the other edge opposite to it, my with increment, that is my plus dou my by dou y into delta y. So we have represented first the bending moments, that is mx and my with increments. So now 4 moments are over, that is the bending moments. Okay, now on this diagram, let us try to represent the shear moments, that is shear bending moments already we have represented. Now let's try to represent the shear stress, shear forces or shear moments. Okay, so and when it comes to the shear moments, we know that shear moments, or we can call it as twisting moments. So these twisting moments usually they act parallel to the surface. Okay, so let's first try to apply this one. Now let us assume on this one mxy. So mxy is the twisting moment is applied on this axis, that is parallel to x-axis. Okay, and now on the opposite edge, that mxy twisting moment is represented with respect to increment, that is mxy plus dou mxy by dou x into delta x. Okay, now similarly another twisting moment is mxy, which is represented again on parallel to, that is x-axis, and then when it is applied on the other edge opposite to it, and you have mxy plus dou mxy by dou y into delta y. Now here we got again 4 twisting moments. So the 4 bending moments are over, 4 twisting moments are over. So this mxy is the bending moment, that is twisting moment applied parallel to the, which plane we can consider this parallel to, or it is applied parallel to x-axis. Now this mxy here is applied parallel to y-axis. Okay, so these mxy will give increment, and again this mxy will give another increment. So totally there are 4 twisting moments along with 4 bending moments that are applied for the thin plate, that is for the small lamina. Okay, now after this, now let's try to extend the other try to add the other forces also. So bending moments are over, twisting moments are over, and the next one is we are adding the shear forces. And we have seen in the previous equation, previous slide, that transverse load, that is whatever we are applying Q, it produces transverse shear forces. Now let's try to see that where we are depicting these shear forces. Now, so Qx, now you can see here the Qx from the center of the plate. Qx is the shear force acting, and it is acting in the upward direction. So Qx is the shear force acting in the upward direction. Now on the opposite edge, the Qx, it is acting downwards, that is Qx with increment, that is Qx plus dou Qx by dou x into delta x. Similarly, Qy is the another shear force that is induced due to the transverse load, and on the opposite edge, and Qy with increment you can able to see here. So Qx with Qx increment and Qy with Qy increment. So these are the shear forces that are induced because of the transverse load Q. Now ultimately, so along with all this, there is already shear transverse load that is placed here, which we are applying on the thin plate. Okay, so if you see, so we are going to represent 4 bending moments, 4 twisting moments, and apart from this, we are going to represent 4 shear forces. With along with this, we are going to represent Q also. Okay, along with this, we are going to represent Q. So 4 bending moments and 4 twisting moments and 4 shear forces. Along with that, we are going to represent transverse load Q on this diagram. So these are the things which we are going to incorporate in this diagram. So everyone must clearly understand these notations and where we are applying and what edge we are applying, at which length we are applying, everything that we have to understand from this diagram. So once you clearly understand this diagram, and it is easy for us to go into the derivation and write equations of equilibrium, write moment equilibrium and all. Okay, so let's move on to the next slide. Now, so these are the equations which we already know from the previous sections that we have, that is bending and twisting. So we have seen that mx bending moment is equal to integral minus t by 2 to plus t by 2 sigma x into z into dz, and we have seen that my is equal to integral minus t by 2 to plus t by 2 sigma y into z into dz, and mxy, and here you can see mxy is equal to minus mxy, because it is nothing but complementary nature of shear stresses, that is the shear stress which may be equal in magnitude but it is in opposite in direction. So mxy equals to minus myx, that is equals to minus of minus t integral minus t by 2 to plus t by 2 tau xy into z into dz. So these are the sections which we have seen in the previous sessions. Okay, and similarly, in the same way like how we have represented mx, my and mxy, similarly let's try to represent the shear forces also. Okay, so shear force qx is equals to integral minus t by 2 to plus t by 2 tau xz into dz. That means nothing but the shear force induces shear stresses. Okay, and we are trying to write this equation with the help of the previous diagram, and we are taking one small element, and through that it induces shear stresses. So the shear stress, when it is multiplied with the dz, it becomes the shear force per unit length, and when it is integrated, you are going to get shear force. Similarly, on the other edge, we can represent the shear force qy, that is equals to minus t by 2 to plus t by 2 integral over tau yz into delta z. Okay, now after writing all these things, now let's move into the equilibrium. So for the equilibrium of the plate parallel to OZ axis, and assuming that weight of the plate is included in Q. Okay, so we are going to consider the equilibrium of the plate parallel to OZ axis. So first let's see where is OZ axis. So now if you consider, and that we have seen that this is, you can consider it as in x-axis, or else you can see in this diagram this is considered along x-axis and this is y-axis. So z-axis is vertically acting downwards. Okay, So similarly in this diagram, z-axis is nothing but what is vertically acting downward. So we are considering equilibrium of the plate parallel to OZ axis. Now when you consider the equilibrium of the plate parallel to OZ axis, that is downward direction, okay, first what we can see here clearly that the shear forces that will come. So Qx and with Qs increment, and Qy with Qy increment, and this Q is there. So these are all the forces which is parallel to OZ axis. Rest of all either parallel to X axis or parallel to Y axis. Only these forces are parallel to Z axis. Now let's try to write these equations as an equilibrium equation. So how we are going to write? If we assume the Qx increment as positive. So let's try to write this one. Qx plus dou Qx by dou x into delta x. But this is the shear force. We have assumed shear force per unit length. Now this shear force is acting on which edge? This edge. And this edge length is how much? Delta x, which is parallel here. Sorry, delta y, which is parallel here. So while you write the equation, you are going to write like this. Qx plus dou Qx by dou x into delta x is the shear force per unit length, and therefore you have to multiply the length on which it is acting, that is nothing but delta y. Okay, and on the edge opposite to it, you are going to write easily that equation as Qx into delta y. Okay, so similarly you have to write the other equation of equilibrium also, that is with respect to Qy and Qy increment. Okay, so let's try to see this. Yeah, now so Qx plus dou Qx by dou x into delta y, that is Qx increment, and on opposite, since we are considering this as positive, and the opposite edge we can consider it as negative, minus Qx into delta y, plus now Qy increment also is acting downwards, which we are considering it as positive. Qy plus dou Qy by dou y into delta x, that is, and on the other edge we are going to get minus dou Qy by delta x. And apart from this, the Q is a transverse load which is acting downwards. So Q is the transverse load. Usually we take load per unit area. Okay, so therefore the Q should be multiplied with respect to the, so Q should be multiplied with respect to the area on which it is acting. So area of the element, we know clearly that it is nothing but what? Delta x into delta y. So Q should be written as Q into delta x into delta y, which is equal to 0. Now from all these equation, you can try to reduce the equation which Qx into delta y and cancel out with Qx into delta y, Qy into delta x cancel out with Qy into delta x, and then you left with the equation dou Qx by dou x into delta y plus dou Qy by dou y into delta x into delta y minus plus Q into dx and delta x into delta y, out of which you can take delta x and delta y common from the complete equation and you can send it equal to 0, and then the above equation simplifies to dou Qx by dou x plus dou Qy by dou y plus Q equal to 0. So this is the equilibrium equation parallel to OZ axis what we got here. Now remember that in this equation, Qx is the shear force along x axis and Qy is the shear force acting in y direction. So these two are very, very important. Now the next equation we are going to write moment equation. Okay. Now moment equation, we are going to take the moment about x axis. Now when you take the moment about x axis, again look out this direction, we are taking moment about x axis. So whatever the forces that gives moment about x axis, so all that we need to consider. Okay, moment about x axis. So what are the forces that are giving moment about x axis? So if you look at this equation, what we got? Mxy into delta y and mxy plus dou mxy by dou x into delta y, and here also even the twisting moments also we are going to apply. We are considering as mxy is a twisting moment per unit length. So therefore we have to multiply it with respective unit length, that is mxy into delta y. Okay. Similarly mxy increment with delta y. Similarly my with the edge length, that is delta x, and my increment with edge length, that is delta x, and then shear force, that is Qy, because we have to consider all the forces which gives moment about x axis. So Qy plus dou Qy by dou y into y into delta x delta y, and Qx. So Qx into, here it is, this is important to understand, Qx into delta y is the force, that is qx per unit length, and we are multiplying with the particular length, that is qx into delta y. And since we are writing moment, you have to multiply the perpendicular distance, and that perpendicular distance from the diagram is nothing but delta y by 2. Okay, so which you can see in the diagram. So qx is the force, and which is acting on which length? Delta y length. So we are going to write qx into delta y is the force equilibrium parallel to the x-axis. And then when you are taking moment about x-axis, and you can see clearly that the perpendicular distance is, you can consider it as delta y by 2, half of the distance. It is acting at the half of the distance. So the perpendicular distance is delta y by 2. Okay, so now here similarly on the other edge with the qx increment, again it is the same delta y into delta y by 2. And when it comes to the distributed transverse load, and we'll write it as q into delta x into delta y. Now it becomes a force, and delta y by 2 is the perpendicular distance. So you are going to get q into delta x into delta y square by 2, that is equal to 0. Okay, so how we are going to take the positive signs, negative signs means it is depends. If you can consider all the anti-clockwise movements are positive, so that the clockwise movements you can consider it as negative, or you can consider clockwise movements as positive, so that the anti-clockwise movements you can consider it as negative, vice versa. So anything you can follow, that is your notation. So finally we end up the taking moment about the x-axis as this equation. Okay, and then this equation is further simplified, that mxy delta y we cancel out with again this mxy into delta y, myx cancel out with this one, my into delta x cancel out with my and delta x. And again if you see here, qx also cancel out here. Okay, and similarly here one more term that is missing is nothing but qy into delta x square by 2, that is also missing. So that will all cancel out. So when you cancel out all the things and try to reduce the equation of this equation, you are going to get dou mxy by dou x minus dou my by dou y plus qy equal to 0. So we are also removing neglecting all the higher order terms, so that you are going to get this equation in the simplified manner. So dou mxy by dou x minus dou my by dou y plus qy equal to 0. So this is the equilibrium equation when you take moment about x-axis. In the similar manner, we can write the equation of equilibrium and when it is taken moment about y-axis. Okay, so the notations will interchange, that is dou mxy by dou x here, so dou mxy by dou y, dou my by dou y here, and dou mxy by dou x here, qy here and qx here. So these are the equations of equilibrium. So first equation, when you see, this is the force equation, that is equation of equilibrium in z parallel to z-axis, and here moment about x-axis and moment about y-axis, which you can consider. Okay, next, now after getting all these things, now we know that from the equation 1, that is dou qx by dou x plus dou qy by dou y plus q equal to 0. So let's try to substitute for this qx and qy from equations 2 and 3. Okay, so now from equation 2, let's see here, from equation 2, qy we can write it as minus dou mxy by dou x plus dou my by dou y. From equation 3, we can write qx as minus dou mxy by dou y plus dou mx by dou x. Okay, so let's try to take qx and qy from equations 3 and 2, and let's try to substitute in equation 1 in place of here. Okay, and after substituting for qx and qy, remember that whatever we are substituting, that should be differentiated with respect to x, and qy whatever we are substituting, that should be differentiated with respect to y. Okay, and when it is written like that, and the equation reduces to this form, that is dou square mx by dou x square minus dou square mxy by dou x dou y plus dou square my by dou y square, again minus dou square mxy by dou x dou y, that is equals to minus q. So these two terms you can add up, and you can write the entire equation as dou square mx by dou x square minus 2 into dou square mxy by dou x dou y plus dou square my by dou y square, that is equals to minus q. Okay, and in the starting of this session, we have already seen the equations for mx from the bending, mx and my from the bending case, and the equation for mxy from the bending and twisting case. Now let's try to substitute mx and my and mxy into this equation, and which gives the entire equation in terms of deflection of the plate W. Okay, so replacing mx, my and mxy from the bending and twisting equations, and if you substitute here, you are going to get the deflection, final deflection equation, that is dou power 4 W by dou x power 4 plus 2 into dou power 4 W by dou x square dou y square plus dou power 4 W by dou y 4, that is equals to Q by D. So this is the general partial differential equation when the plates are subjected to distributed transverse load Q. Okay, so this equation we need to remember. Even most of the numerical problems also, the question will be asked that the plate is subjected to distributed transverse load, and he will ask you to find out the deflection form of the plate. Okay, so in that case, this equation is very important to remember, and he will just try to give you the deflection shape, like W equals to summation AMN sine M pi x by A sine N pi y by B. He may give like this, or he may give any form of the deflection equation. So in that case, we have to substitute here. We have to ensure that the given differential equation, that is the given deflection equation, should satisfy this equation. Okay. Now the above equation also, again further it can be written as, in terms, you can reduce it to dou square by dou x square plus dou square by dou y square of dou square W by dou x square plus dou square W by dou y square. Now from this also you can take this W out of this equation, so that both the equations will become same, and we are writing it as again dou square by dou x square plus dou square by dou y square whole square of W, that is equals to Q by D. Okay, and this dou square by dou x square plus dou square by dou y square is nothing but known as Laplace operator in 2 dimensions, and it is sometimes written as delta square like this. Okay, so delta square, and again one more square is there, so it is nothing but delta square whole square of W, that is equal to Q by D. Sometimes when the derivation is asked, straight away he'll give you delta square whole square, that is equals to Q by D. Okay, so he'll ask you to prove this equation, so you should know what is this delta square, which is nothing but the Laplace operator. Okay, so this is the equation of the partial differential equation in terms of deflection of the plate W, and in terms of the Laplace operator delta square of square into W, that is equals to Q by D. Okay, so that's all from today's session. So let's meet in the next session in the topic general solution for a thin rectangular plate. Thank you.